Let's suppose we have a plane and there's a point, call it point Q, and we want to know what is the distance of Q from the plane. Well, we know that a plane has a normal vector, and we could pick another point on the plane and make a vector from the point on that plane, this point P right here. We could make a vector from P to Q, with P the initial side and Q the terminal side. Now we've got a vector from P to Q, and we've got this normal vector here. Now let's think about this. What if, let's look at this line right here. This is the distance. Think of the length of this little broken line right here. That's the distance from the plane to Q. What if I go 90 degrees from this little broken line over here to the normal vector? What if I do that, like that? Well, that gives me a point on this normal where I could make a vector. In other words, I've got this P here. I could go up and make another vector up to that line. In other words, where this line goes over and hits this normal, I could say, okay, there's a vector that starts down here on the plane and goes up to that little broken line. Well, if you think about it, the magnitude of this vector right here is the same length as this right here, is the same as this right here, right? In other words, this length here and the length of this vector are the same. Well, what we just did was we talked about a projection. I'm taking this vector, PQ, and projecting it over to the normal vector N. So that's the projection of PQ onto N. So that's what we want to look at now. So you can see sometimes there's a need to do a projection like this. So let's think about, before we get going, let's just think about something here that we're going to use in a minute. Let's suppose we have a vector. It's just got components v1, v2, and v3. And think about what would happen if we dotted that vector with itself. We got v dot v. Well, it would be v1 squared plus v2 squared plus v3 squared. Yeah. See? Because v1 times v1. Yeah, you can see how that works. Now let's think about the magnitude. What if we did the magnitude squared? In other words, this thing. What does that look like? Well, we've got the square root of v1 squared plus v2 squared plus v3 squared. If we square that, we just get this. Well, heck, that and that are the same. These two things right here are exactly the same. So what we found out is whenever we see a vector dotted with itself, we can replace that with the magnitude of the vector squared. Okay, so that's just some things that's just something I'm going to refer to here in a minute. But what I want to do now is see if we can figure out how to project one vector onto another. So let's suppose we've got this vector u and we've got a vector v. And what I want to do is I want to project u onto v. In other words, if we extend a line up from v like this, I'm wondering how far up do I need to go so that I can go 90 degrees over and hit the terminal point on this vector. That's what I'm trying to do. I'm trying to find this vector right here, this little green vector. Now you can see what's involved here. Really, we're not changing the direction of v, we're just changing the length of it. So I'm going to call this green vector here CV. CV. It's just the vector multiplied times a scalar which changes its length. And what I need to do is I need to figure out what is C. So this right here is the vector we're looking for. We're looking for this green vector. And what I need to do is figure out a formula for C. In other words, how much do I need to multiply v by to get that vector, to get the projection? So let's think about this. Let's think about what if we subtract u minus cv? Well, it looks like this right here. And remember, the geometric interpretation of that is you have the initial point here, and it goes up to the terminal point over here on u. So this is a geometric representation of this u minus cv. Okay, we didn't have to have that, but you can see it's a cv and u minus cv are perpendicular. They're orthogonal, right? You can see that. Orthogonal vectors right here. Okay, now let's do this. Let's dot product V with U minus CV. Now notice V and U minus CV are orthogonal, right? See that? This green vector here, the V is the same direction, so these two vectors are orthogonal, right? That means their dot product would be 0. So I'm just dotting V with U minus CV, and I'm getting this 0. Now let me do a little algebra here. If I distribute the V through here, I get U dot V, see, minus C V dot V. See, just a little distributivity. Now, look what I have here. I've got V dot V. Well, we discovered a minute ago that that is just the same as the magnitude of V squared. Okay. Now I'm solving for C. So if I solve for C, look what I get. I bring the UV over. Well, if I take this to the other side and then divide by the magnitude of V, I get this. This is what C is. Now remember, the projection is CV, and we needed to find out what C is. We already know what V is. V is the vector. So now we get this. We get the projection of U onto V. This is the way this is read. The projection of U onto V, which equals CV, is equal to U dot V over the magnitude of V squared, this right here, times V. See, this is the C. This is the C part right here, times V. See? That's the projection right there. So the projection of U onto V is that formula. Now, let's see how this would work in practice. We've got this vector U, which over here, if I just plotted it, it's at 3, 9. This point right here is 3, 9. So this vector U we could write as 3, 9. The vector V is 1, 1. See that? 1, 1. I just, looked at what the coordinates were. Now let's use this projection formula. We've got U dot V. Well, that's the top here. See, 3 times 1 plus 9 times 1. All over the magnitude of V squared. Well, here's the magnitude of V squared, and that's just going to be 2 times the V vector. Okay, so what we have is the projection is equal to 12 over 2 times the V vector, which is 6, 6. Now, dig this. That 6, 6, that's exactly this point right here, right? 6, 6. That's that point. So what we've done is we've found the projection. And that's what we want it to do. But it's all about using this formula.